Okay, here we are. I'm Jeffrey Fox, and we're on the fourth of these sub-lectures in the Hadoop and MapReduce section of the class, our cloud computing class. So let's get going, and we're going to go through things like MapReduce, um, Yarn, and the other critical shuffle and so on, which are the components of Hadoop. If you look at Hadoop, it has several core components, some sort of general common software. This is a software engineering statement. It has the very important HDFS, because I said that's likely to be the part of Hadoop that survives changes. It has the resource manager, Yarn, which is split off in Hadoop 2. Hadoop 1 integrated Yarn and MapReduce together, but now they've correctly separated it so that you can actually build Hadoop with Mesos or Kubernetes, and you're not forced to use Yarn. And then MapReduce actually has the programming model. Yarn schedules the tasks, HDFS describes the backend disk system, and the MapReduce component does the programming for you. Okay, so here's this architecture of HDFS, which you pointed out was a critical component of Hadoop. We have the user. There is a name node, which actually tracks the metadata, which describes where things are. And then we have data nodes, which actually store the data, which is either replicated or has some sort of redundancy, parity check built in. And the name node in the latest version of Hadoop is replicated for fault tolerance. So, and we've already, I believe, described how the key idea in Hadoop is to take every piece of data, take your data set, chop it up into blocks, which originally were very large blocks, 128 megabytes, but now are much smaller, so that they can deal with small files. If you have giant blocks, then you're not going to be able to deal with small files very effectively. Anyway, each block is replicated 3 times in the standard Hadoop. All right, so here is the overall architecture. We have Yarn, the resource manager. We have this marvelous name node, which is looking after the data and controlling the backend file system. We have a application master, which is running the actual application. Every node has a node manager. And then we have this uses the word slave. I prefer the term worker. This is a master worker framework, not a dictator slave framework. And then we have every node has its own manager, and they're done in parallel with these capabilities up here. This is in Hadoop 2 and 3. This slide has got the same structure as the previous one, but gives more detail. We see the application manager as part of the resource manager and the scheduler as part of the resource manager. We have each data node is done now in a modern fashion with containers, which in Hadoop 3 are actually Docker. And so we have a nice model which is compatible with the overall philosophy that you build everything around containers and use technology such as Docker to manage those containers. And then the containers each node has its own set of containers. So this slide describes how Yarn, the resource manager, fits with the rest of Hadoop. The clients, or several clients, can access a given resource manager. Every node has a node manager. And then we have the application master, which is specific to the application, and it manages containers on multiple nodes. And we have a pink job with an application master here, and a purple job with an application master here. And they all have containers which are either on the same node or on different nodes. And so the resource manager manages this complexity. And they all send messages back and forth to keep track of what's going on. So this sort of says what we already showed in the pictures. There's a scheduler and an application manager in the resource manager with the scheduler. Notice Linux, or let's suppose you're running Linux on these machines. Linux actually does the hard work. It decides which tasks to run when, and whether a task is waiting for disk or not. What the scheduler does is just assign tasks to cores, and then ask Linux to do its thing. And those schedulers, there's a huge amount of work, far too much work on schedulers, because the reason people write scheduler works is it's about the only part of the system you can touch as a user. It's not particularly the most important, in my opinion. I think what Linux does is the most important. How you decide when to stop a task and restart it and things like that. So there's a reservation system, as in classic scheduling system. Say the different scheduling strategies, and trying to be fair to jobs, or trying to maximize the largest job and things like that. And they say you can plug and play with those, but most people just leave them as they are. I mean, I have written papers in this area, and we have an application manager which accepts the job submissions and sets up the containers. And it also restarts failed containers. All right, so an application consists of a set of tasks, both map tasks and reduce tasks. And the input data to the map task is stored in HDFS, possibly through HBase. And there are various input format specifications, which which is also doing the splitting, because you want to remember partition the data to do parallel computing, and you do an input split, and then you assign one input split to each map task, and it provides the input split allows the job to read in a stream of bytes, which are then key value pairs, and you have a block of data which is multiple key value pairs. You need to have lots and lots of key value pairs in one split, because otherwise the overhead of chopping it up will be too much. You don't want one key value pair in each split. You want 10,000 or some largest number, so the overhead of splitting it up is not too high. Another possibility you could do is have more map tasks than there are cores. Then you could split everything up and have some of the maps not running. That gives you more chance of actually balancing the load if the maps have different capacities. Because if a short map task finishes, you can then reschedule it with one of these other ones that's been waiting, because you assigned, say, 4 times as many map tasks as there were cores. So this slide puts in writing some of the things we've already been saying. Describes the application manager, which used to be called the job tracker, or at least was part of what used to be called the job tracker in Hadoop 1. It schedules and assigns map tasks to cores or map slots. It implements the map operation. And there's a partitioner, which decides which key will be processed by which mapper or producer, and he uses a hash function to do this. There is a combiner, which used to, for some reason, is called a semi-reducer, and it is basically a thing that cleans up the results on a single node to reduce the amount of communication between nodes. I mean, we've had an early example where we had, I think, a couple of cars from one node. You'd want to add those cars together on the node rather before you sent them out, because communication is expensive, and adding things on nodes is pretty cheap. This is a general principle of parallel computing. Here is a general picture of what's going on here. We have moving the data from the map task to the reduce task. Here's the mapper. Results of the mapper here. This goes to a shuffler and a merge, which are basically preparing the data these key value pairs in ordered fashion so that they can be efficiently reduced by the reduce tasks. And then those reduce tasks store everything on HDFS. These things up here are also stored on HDFS. They're the results of the map tasks. Reduce is also, logically it's the same as a mapper, except it just does a different task. It runs in parallel because you can add things up. And let's take the simplest reduce we saw, adding up the counts in word count or adding up the number of events in a histogram bin. Those can all be done in parallel. And there are actually quite clever algorithms to do such so-called reductions in parallel. In general, it requires fewer reduce tasks than map tasks, although in the highest performance implementation, MPI, there are exactly the same number of reduced tasks as map tasks. So it's, but Hadoop has a much stronger separation between map and reduce than MPI. In MPI, they're all merged together, which makes this efficient. Shuffling, I've already mentioned that shuffling is needed to make certain you get to each reducer the data it wants. It effectively sorts the data using HTTP to fetch the data off disks, and it is waiting for the map task to finish. And it uses copier threads, which actually do this task of reorganizing the data and sending it to the right place. Here is another example of this. We have the mappers. They produce key value pairs. And they are sorted and sent. They're merged together as needed for the reduction. So each reducer has the data it wants and only the data it wants. The reducer will often just say it's given 1,000 keys. It will add up the values for each of those 1,000 keys. This other reducer will have another set of keys, or sometimes which could be in some keys are shared between reducers. We saw that with the juice example, where the orange key got sent to multiple blenders. Here's a rather nice picture about the overall architecture with the mappers, the sorters, the shufflers, and then on the next slide we have the shuffler. It's just as repeated, the merging of the results from the different shuffles, and then finally the reduction. So this is actually quite a high-resolution picture. So I don't think it's useful to go through it in these slides. You can just study this in detail. There is a link if you want to just bring it up on your computer in its original fashion. Here I've chopped up a single original picture into two parts to fit on the slide. So the group, the merge is fetching everything by key, and there are merging threads which do that. And this is very specialized to this particular problem. The more general previous parallel computing technologies did not have merge, shuffle, or sort phases, because that's very particular to this problem. Here we have the reducers, which are very straightforward. There's the user specifies the output format, and the reducer does its thing. Notice in many Hadoop jobs, it's done pretty inefficiently. You just have a single reducer, which adds up the results of all the maps. That is extremely inefficient. It's much better to do parallel reduction. Because if you're summing from 1 to 1 billion, you can actually take it in groups of 1,000 or 10,000 and add up whatever it is, 10 to the 5th reduced tasks, each of 10 to the 4th numbers. That will be a wonderful parallel job. There is an output format defined in Hadoop when you specify it. The usual output format is key value pairs, but there are some other ones for sequence files and no output, and also a streaming example. All right, so these are all things you specify when you run your Hadoop job. Okay, so that's the end of this section. Thank you.